I'll be presenting on the Drought Index use case that we've been working on with Edward and David. We'll start off by defining what drought is, and the easiest definition that I found was that drought is a period of time when an area or region experiences below normal precipitation for that specific area. So I'll post a link in the chat for the National Geographic entry that I found that gives a good introduction on drought and the effect of drought and sometimes the difficulties of trying to measure drought using Earth observation data. Now, the most notable effects of drought that are common to areas is that the lack of precipitation, which is the major issue with drought, causes the crops and other vegetation to dry up, and also causes reduced soil moisture. That's the drying up of water in the soil, and the drying up and diminishing of the water sources in an area. These include lakes, rivers, streams, and groundwater. Now, measuring precipitation in itself does not give is not a complete indication of drought, but we can also measure these effects that I've mentioned of drought. So we'll be using the following data set in trying to define a good method of how to monitor drought. So for precipitation, which is the major definition of drought, we'll be using the rainfall estimates from the CHARPS data. For the water extent, which as I mentioned here before, is drought causing a drying up of water sources, we'll be using the WRF's feature layers. Again, the other effect for drought is the drying up of crops. So this is the vegetation health. So we'll be measuring that using the climatology data set for the NDVI, and also the calculated NDVI from the Landsat and Sentinel-2 data sets. We'll be also trying to measure drought using changes in the land cover classes of an area. So we'll be using the fractional cover data set for that. And for the soil moisture, we'll be using the global root zone moisture analysis and focusing system. That's the graphs data set. Now, with that introduction, I'll be demonstrating the notebooks that we have. Try to zoom in a second. Okay. So for the rainfall measurement of drought, we'll be deriving the rainfall anomalies from the CHARPS data set, and the defining formula we'll be using for all the data sets will be the standardized anomaly, which is defined as the seasonal mean. You subtract the long-term mean and divide by the long-term standard deviation. So for our for the notebook, we'll start from loading the packages and setting up the task cluster, as we do for most of the notebooks in the sandbox for analysis. In the starting area, we'll be trying to load the climatology data set, which will serve for our where we'll get our long-term mean from, and also our time period of interest data set, which is where we'll get our seasonal means from. As you can see here, for the rainfall, we'll be using the DS RFM. That's the variable we'll have named our climatology dataset, and the DS RFX will be our, I'll say, the anomaly dataset. Now, these notebooks are focused over the analysis of counties of Kenya. So the default county we've chosen at this time is the county of Turkana. Now for a climatology data set, we have data for a period of about 30 years. So in this case, we used 1984 to 2014 for the climatology data set. And then the period of interest that we want to see or find the measured drought for is the 2021 to 2022 year. So for this case, it will be January 2021 to the most recent, which is May of this year. A specific thing to note in the notebooks is that here the CHARPS dataset has a pretty large spatial resolution, so that will run fine. But in other datasets, due to computing power, we will need to increase the resolution. That means we won't use the native Landsat 30-meter resolution. We'll use about 120 meters. And all the results are being saved into one folder. This is the results folder. Here we'll load the Kenya's county shapefile, which is provided in the data. I saw on the group invite that Edward had posted a link to the specific branch on the Sandbox repository. If Edward, you could post it again on the chat, then if anyone would like to follow along on their own Sandbox notebooks, then they'll be able to do so. So you can adjust this analysis for different counties of Kenya. So here I've printed out the unique 47 counties in Kenya. You can just copy any of the counties from here and replace this variable here in county and rerun the notebook for that specific county. Now, next we'll load the rainfall data. So we've created a query here that loads data specifically for the county we've defined and for the time period that we will have the climatology time period. So this DSRFM is the climatology dataset, and DSRFX is the dataset for the time period we want to calculate the anomalies for. Also, you'll notice at this, if you in the slides, I have attached the links to the data specifications guide in the docs page for DAfrica. So you'll notice that this data set specifically has this no data value. So we want to convert them to none. We will do that for both the data sets. Another step in pre-processing our data is also masking it specifically to the county. And we'll use this mask, this section for masking. The next section is getting the total rainfall for each season. Now, you'll notice in this area, we've resampled the data set to seasons, which we've defined as 3 months. One season is lasting 3 months in a year and calculated from the past season beginning in January. All the plots are saved into the results folder. So if you wish to revisit them after you've run, it's a simple matter of importing the images into a new notebook. So these are the per pixel total rainfall for the county from 2021 to 2022. We have also aggregated, that means gotten the mean for the entire area. So for ease of analysis, so we have the total rainfall for each season, starting from 2021 to 2022. Please note that these dates are just indicative of the beginning of the season. So for this first season begins on 1st of January, and the next season begins on 1st of April. Now, in this section, we'll be calculating the rainfall anomalies and the standardized anomalies. Now, the difference between the rainfall anomalies and the standardized anomalies is for the rainfall anomalies, if I go back to the formula that we have up here, is that the anomaly is simply the seasonal mean minus the long-term mean. But the standardized anomaly is the seasonal mean minus the long-term mean and over the standard deviation for the long-term data set. So in this section, we calculate the climatology mean and also the standard deviation for the long-term data set, and then use this in this next section to calculate the per pixel anomalies and the standardized anomalies. As you can see here, we've plotted them out. So we have the anomalies for the year 2021 and the year 2022 for each season. So we have these seasons are named here as quarters. So we have the first, second, third, and fourth season for 2021. And since we've not yet ended the year, we only have data for 2 seasons. So that's January to March 2022 and March and April May, the season for April, May in 2022. Again, also this is not a complete season because for a complete season it would be required to be April, May, and June, data for June. We also have, so that's the rainfall anomalies, and these are the standardized anomalies. And as you can see, this area has is quite a large deviation from the trend, and the trend in this case is defined as the mean, especially for this most recent season. We also aggregated the same seasonal, the standardized and the rainfall anomalies. So this is aggregating them over the entire area. So we have a single value as a representative. So in this case, we have the rainfall anomalies for each season, which will later export as a CSV. And we also have the standardized anomalies for each season, also as a singular value. Here we plotted the total rainfall. So you can see there was quite an increase in rainfall between March and the season of beginning in March and the season beginning in May, but there's quite a huge drop between 2021, that's the season beginning in September, and the season beginning in September and the season beginning in around November. We also have plotted the rainfall anomalies here and here. So we can see there's a negative decrease, a decrease from the mean in these seasons, but quite a huge increase from the trend in the latter part, in the later seasons. That's the season beginning in March of this year. Are there any questions so far?
Thank you, Victoria. Just one question from Tina Babe in the chat.
I can say verbally. Can you go back to the last season of 2022, the one spatially distributed? Yes, this one. I was just wondering, how come you have mentioned that the last season of 2022 is not even complete, but we just see the high rise in terms of value So even if it's also not complete, I expect a bit even less than getting higher. How is it resulted like that?
So what happens with the resampling is that it, in this case, is the entire mean is calculated for data spanning the 3 months for the complete seasons. But since we are in June, it only calculates the mean for that's April and May.
So it's only the mean, not the anomalies.
Oh, sorry, I mean the anomalies. We started off by calculating the mean for the seasonal mean, which is what we use to calculate the anomalies. So the seasonal mean used here, unlike in these places where it's the seasonal mean for data for 3 months, in this case, we only have data available for May, is it April and May? So that's what's been used to calculate the anomalies in this case.
So thank you, Victoria. At least Tina Babe, it's every quarter, and also recognizing that Tina Babe is from WRI. She's based in Ethiopia, a geospatial scientist, and she's been working on this field for a while. And we thank you for your comments, Tina Babe. I'm a signalo.
Thanks, Kane. Yeah, the answer, I've got the answer. Thank you, Victoria.
Welcome. Are there any other questions, or we move to the next notebook?
Hi, Victoria. I think I just want to make one comment regarding
Yes.
the distribution of the seasons and the quarters. I think for this particular case, we are using the 3-month quarters. But again, we understand that countries have different climatic, rainfall patterns. Where, for example, within Kenya, we have the long rains in March, April, May. Then we normally have, negligible sort of rain within countries, that is June, July, August, September, then October, November, December is another rain. For this particular work, the distribution has just been done in 3-month quarters to make season.
Thank you. Right. Now we'll move to the water observations from space anomalies. So we're calculating the deviation in the water extent for water bodies found in a particular county. So the same principles that we used in the rainfall anomaly notebook is the same as used here. So we'll start off by loading data for the climatology time period. That's 30 years. That is 1984 to 2014. And we'll also load the data sets for the anomaly time period. So that will be 2021 to 2022. Like I mentioned before, in this case, we'll increase the spatial resolution so the kernel doesn't crash. So we'll be using the 120 meters. Again, you can select any county from the list of counties provided here. So all you have to do is copy your county of interest and paste it here, and then rerun the notebook. And the water threshold is specific to this Wolf's anomaly. So what this value represents, as we'll see later, is whether if a pixel has a value above the water threshold, then that pixel is classified as open water, but it has a value below the WAF's this WAF's water threshold, then we will classify the pixel as land, and more specifically, simply not water. Now in this section, we will now load our wolves data, and the specific data we're using is the wolves feature layers. Again, in the presentation, I provided a link to the data specifications in the data catalog for this data set. So we load the wolves for the climatology period and the anomaly time period here. The next part that's for the wolves is masking the data set. So we want to identify pictures that were classified as clear, that is free from cloud data interference, and also classified as wet. So we have the clear and wet pixels, and we have the clear and dry pixels. Now, from the worst, we want to calculate the feature layers. We want to calculate the frequency with which a pixel was classified as wet within a time period. So that means the frequency is the number of clear and wet observations that a pixel has over the number of total clear observations. So clear observations are clear and dry plus clear and wet. Like in the rainfall, we'll resample our data sets to the 3-month season starting from January, and then we'll get the frequency. So here we have the clear observations, which are the number of clear and wet observations plus the clear and dry observations, and then get the frequency with which that particular pixel was classified as wet in a season. So we have the clear and wet observations over the total number of clear observations. In this next part, we'll mask the data set, the frequency data set that we have obtained in this previous step using the county boundary as we did for the rainfall anomalies. Now in this part, we use the water threshold to get the pixels that we will define as open water. So if a pixel has a frequency above the threshold that we've defined as 0.5 at the top, then that pixel is classified as open water and as regular open water. From this regular open water, we can now get the extent of water in the county, which will, as you can see here, we have the water extent in kilometers squared. So this first cell is to get the area per pixel. Then since we have the pixels which were classified as water, we simply multiply by the area per pixel to get the water area extent for the county in kilometers squared. Again, the dates here are to mark the start of a specific season. So here we have the 1st of January 2021 to mark the first season in 2021. Now from this water extent, we will get the mean, the average for each season over the 30 years, and we'll also get the standard deviation for the water extent for each season over the 30-year time period of 1984 to 2014. Using the climatology datasets and the seasonal datasets, we can get the water extent anomalies and also the standardized anomalies. This cell is specific to just transform the dataset to a pandas data frame, which is easier to export as a CSV for later analysis. So in this case, we have the water area anomalies, and we also have that's simply seasonal mean minus the climatology mean, and the water area standardized anomalies. This is the seasonal mean minus the climatology mean over the long-term standard deviation. Again, we put them all together in one data frame and plotted it over time. So in this plot, we have the water extent for Turkana County from 2021 to 2022. As you can see, there is an increase over the time period. And we also have the water area anomalies and also the standardized water area anomalies for the same time period. We've exported this last cell. You'll notice in most of the other notebooks, we've exported the data sets later to be able to use them to come up with a proper drought index. Any questions so far? Okay, then I'm guessing silence means I'm not lost everyone yet. So we'll move to the vegetation anomalies notebook. So for the vegetation anomalies notebook, we'll be using the NDVI climatology dataset. In this case, unlike the rainfall and the WRFs anomalies, we don't have to calculate the climatology mean and standard deviation. We don't have to calculate the climatology mean and standard deviation because we already have the climatology NDVI dataset provided. So again, we have the packages to import, the Dask, setting up the Dask cluster, and defining the variables, the time, resolution, CRS, and the results folder where we're going to store the results in. Now, this specific minimum number of observations is due to the NDVI climatology dataset. So we want to keep observations where the number of clear observations are greater than 20 to 30. So in this case, we picked 20 on the lower side. We also have the water threshold in this case, in which we will classify pixels as either water, open water, or land in order to mask the NDVI datasets and the climatology dataset. So in this next section, we'll first be getting the NDVI from the Landsat and the Sentinel-1 datasets. So we have, we load the Landsat 8 and 9 data available for 2021 to 2022. And in the next section, calculate the mean NDVI for each month in the time period. So in this case, we will have resampled it to, we'll sample our NDVI dataset to 1 month, to a 1 month period. Again, we'll mask our dataset to the county boundary and also generate land mask, which is where the water threshold comes in, where we will pick any pixel that has whose number of observations is, or frequency it's been classified as water is less than the water threshold. Then we'll pick it up as land and use it to mask the NDVI and the NDVI climatology dataset. Due to the how the NDVI climatology dataset is presented, all the months are presented, data for months are presented as variables. Now, this specific function here, the get NDVI climatology, sort of mutates the data set to be able to get the value, the data for each month in a time dimension, which makes it easier to work with when we are calculating the climatology, the standardized anomalies and the NDVI anomalies. As you can see here, we have calculated the per pixel anomalies and the standardized anomalies, which are displayed here. So we have for each month, for 2021 and 2022, the NDVI anomalies for the Turkana County. As you can see, 2022 is not complete because we're currently in June, which is where it stops. We also have the standardized anomalies for Turkana County from 2021. So all the 12 months 2021 and the 6 months for 2022. For later analysis, we have aggregated the climate, the anomalies and the standardized anomalies into a single value that's representative of the entire county. So we have the NDVI, the monthly mean NDVI from the Landsat and Sentinel-1 datasets here. And we also have the NDVI anomalies for the NDVI anomalies and the standardized anomalies for each month for the Turkana County as a singular value. Next up, we have the fractional cover anomalies. So in this case, we only did a per pixel anomalies. So now the fractional cover shows the green vegetation, the proportion of a pixel that is green vegetation, non-green vegetation, or bare soil. So in the faster section, we load the data. Here we load the fractional cover data and specify the proportion for the bare soil, the green vegetation, which is presented by the PVPC, and the non-photosynthetic, that's the non-green vegetation here. Again, we mask the data set to the county and calculate the standard anomalies and the standardized anomalies. As you can see here, this is since the fractional cover is an annual data set, then since we only have up to 2021 as of this moment, so we're able to calculate the standardized anomalies for Turkana for 2021. So the image on the left is for the green vegetation. The image in blue is for the non-green vegetation, and the image in red is for the bare soil. Next we have is the soil moisture. So for soil moisture, we're using the global root zone moisture analysis and forecasting system. That is a graphs. Now this data set is external to the Digital Earth Africa platform. So we do have a function in here to help download the data for the county in question. So we have the surface wetness, which is the soil moisture, and surface soil moisture, and we also have the root zone soil water index, which is derived from the surface relative wetness. This specific function is to download the data into that for the specific county and time period of interest, which is then loaded as a surface wetness dataset or the root zone wetness dataset. Next, we calculate we resample the data to seasonal to a seasonal data set with so that's 3 months for each 3 months per season for each year beginning in January. Again, now here we plotted it out. So we have the per pixel seasonal surface wetness for Turkana from 2015 to 2020. We also have the root zone soil water index for Turkana for 2015 to 2020. the reason that the time period differs from the other notebooks is we couldn't get data for 2021 and 2022. So we stuck with 2020 to give a long-term view of how the soil moisture for the specific county has changed. Like for all the other notebooks, we aggregated the data for over the county to a singular value. So we have the relative wetness and the soil moisture, soil water index as singular values for each season for the years in the specified years. And we've plotted out the trend in this plot. That's it for, these are all the notebooks available for the Drought Index. If there are any questions, you can ask them now.
Thank you very much, Victoria, for this great presentation. Also acknowledging that we've received more persons from Africa Women in GIS, acknowledging the work from Damilola. Damilola, are you able to greet the participants as we wait for other questions? Olufemi. Otherwise, I think now we don't have any questions for Victoria.
I have a question.
Yes, please, Eileen.
Thank you very much, Victoria, for your presentation. I'm currently also working on monitoring droughts in arid areas, and my challenge is, okay, you found great results in different notebooks, but how do we combine it? Because I'm also trying to look at the satellite images and the NDVI and yeah, like the different indexes. And I'm having a challenge to know how to monitor them. Do you have an idea of how we can consolidate the results in order to monitor the drought?
Actually, that's something we were presenting on. The reason we're presenting on this forum is to get ideas of how to combine all these results in sort of a singular index. For example, one of the things I've seen is the SPI that have done the precipitation and I think temperature. So we welcome any ideas on how to get it together into such a format.
Because I'm also looking at, there's a model I'm working on. It's called the Klausmeier model, and it tries to combine different parameters. So it's currently eating my mind. I think we can discuss more on it as we move forward.
Yeah, sure.
Thank you.
Thank you very much, Eileen. Could you paste the model here?
I don't have the model right now. I'm still working on it.
The name of the model. We had
the name of the model. Okay, let me.
Thank you. I have Tina Babe next.
Okay. Just from Victoria's question of an idea of combined kind of index, I was just I thinking we have a discussion a few time back regarding the combined drought index, which is combining precipitation, temperature, and soil moisture data. Soil moisture can also be replaced by NDVI, and then this index integrates both those three parameters. And currently, GRC, Joint Research Center, is updating the drought situation of Europe using this index, as well as we have also produced that using that index by integrating the TRIPS precipitation and then temperature from NOAA and then NDVI spot vigility for IGAD region. And that's actually sent for IGPAC, and it's available in the server that the server already updating it each 10 daily basis, but then the drought is calculated in a seasonal basis in 3 months period. So that's how could possibly be done using the data that you already showed to us, Victoria. I think it's possible. And it's also very interesting to see that drought index being applicable for the whole Africa. And we have tested that for IGAD region and for the Eastern Africa. Looks like it's very, very promising in terms of getting the picking the great 2010-2011 drought situation for that Somalia, Kenya, northern Kenya, Somalia, and southern Ethiopia, and then the drought situation for 2008 in the eastern Uganda is also been really easily figured out using the combined drought index. Yeah, that's it from me. Back to you. Thank you.
Thank you so much, Tinabeb. I'm a Signalo. This is good experience from IGAD to our sisters and brothers also on this side, that we can also see that the example Victoria presented was some area which is semi-arid. Perhaps it could be different for an area which is a different environment or climatology. So these are possibilities, and all our questions and comments are welcome. Just go in if there's any more question for Victoria, and also thanking Victoria for this great work with her team.
I have actually one question.
I have a question.
Please go ahead. After
Yes.
you.
I want to know if you collected any empirical data, like from the field, maybe just using sensors so that you can verify the results.
Sorry, I didn't quite catch the last part.
Yeah, Dr. Kilobugi was asking if you did some field work.
Have you done any field work so that you can verify the model results?
No, we've not done any fieldwork. All data is from the various Earth observation sources.
Thank you so much, Victoria. I know this question was coming, and that's why everyone is on the call. So our researcher and our very own Dr. Kilobogi is able to test some of these results in her area where she visits different field sites. So it's also on the strengths of our team that we develop the science and we work with persons who are able to do some more research on the ground, and we can compare and have empirical results that you can even publish and share with everybody.
Yeah, so Ken, I think one thing that I'm adding it to it is we are working closely with LCMRD, who is also actually in lead of this product that we are working together with them. So Dr. Kalebugli, I think we'll be happy to also have you test this notebook at your area to also provide feedbacks on the results that you get for the area. And we'll be happy for everyone who's on this call to also have access to it, and also share any ideas or any other things that you think you can use to improve this notebook with us. Thank you.
Thank you, Edward.
Okay.
Thank you.
Thank you. Thanks a lot.
Thank you, Dr. Kilobugi and Victoria, and also recognizing that we also have a young career persons from Africa Women in GIS. Some of them, maybe James Mugai. Are you from the University of Nairobi? James Mugai. So recognizing other persons like Martha. I know there's a lot we can do, like in Shinyanga area of drought and etc. Do you have some other areas after you finish the census? Otherwise, thank you everybody for joining us today. The session today is recorded and will be shared. Tina Babe, last comments?
Yeah, I was just trying to ask Victoria regarding the data sets where especially for the temporal resolution. When we were working for IGAD region, our main challenge was the starting period, especially for temperature data sets, which was really not so much available. Like the one that we have used started from 2000, And as you know, for drought, we need at least 30 years and above data. And then how do you come up with this temporal scale, like resolution? I mean, TRIPS is from 1981 until now. And how about I know in DVA also the same, but the others are really not in the same time span. So how do you plan to solve that?
For the temperature, is it possible to substitute with the Landsat surface temperature, or is that too different?
As long as, I mean, it's representable for a temperature, I think so it would be possible. And but what we have used is a very coarse resolution, which is about 27 kilometers. That is a drawback for combining that in, I mean, lots of variables into one index. So you have got a very good product of rainfall in NDVI, but not temperature. But there is a 3 kilometer resolution temperature data, which is from Copernicus, that's released from 2015 onwards. But that is not useful for us because we are more focusing on the long term, at least 30 years and above.
So thank you, everyone. Thank you also for the great questions. And I think we'll put Victoria and Tina Babe in one meeting to continue with these great discussions. So I'm grateful that everyone has joined us. We'll be able to connect next week for a French session. Hopefully